We've been talking about how the sun fuses hydrogen to helium. And so that's part of the natural process of what's going on inside the sun. Once an object forming a protostar begins doing that, it becomes a star. And so at that point, we have a star, and we are now going to be stable. Okay, so stars are stable; they're not keep changing like the protostars do. Well, they're not going to be able to fuse hydrogen into helium forever. There's only so much hydrogen in there, and eventually, once they run out of hydrogen, then they are going to start changing. They're going to evolve off of the main sequence. And so, what we want to talk about is how that happens, because that actually has a lot to do with Earth and the sun, because the sun turns out it only has a certain amount of helium in it, or hydrogen in it, so once all that hydrogen is converted to helium, it quits behaving the way it's behaving. In fact, what we've realized is that even before it runs out of hydrogen, it quits behaving exactly the way it's currently behaving. Now, that's very important because what the sun does affects us here on Earth. So once the sun becomes unable to fuse all the hydrogen into helium, then it's going to start evolving off of the main sequence. And that's going to be devastating to us here on Earth. So our next topic of study is stellar evolution. So this is actually evolving off of the main sequence. And so now this is getting us into chapter 19. The initial mass determines what happens. In fact, it was something called the initial mass function in astrophysics. That if you know the initial mass, you can calculate pretty much what's going to happen to stars. You know, we know how long it takes a star to form. The more mass it has, the quicker it forms. The lower mass it has, the less gravity, and the longer it takes to form. And so that's just a known factor that's going to play into this. The other thing that happens is that low mass stars don't have to fuse very rapidly to hold themselves up. High mass stars have to fuse extremely rapidly in order to hold themselves up against gravity. And so the end result is the high mass stars, even though they have considerably more hydrogen than the low mass stars, they run out of it first. And so so what happens to a star is going to, in part, depend on the mass. That's also going to relate to the lifetime of the star. It's going to relate to how hot the star is once it becomes a main sequence star. You know, the main sequence, we talked about the mass-luminosity relationship. The higher mass stars tend to be hotter. And that's going to be, again, a factor for us to consider in how we look at this. So the sun. After the main sequence, the first thing is, what does it do? Well, recapping, what's going on in the sun now? Hydrogen is fusing into helium via the proton-proton chain. And so the proton-proton chain is fusing hydrogen into helium. And so that's what's going on inside here. You start with 2 protons, becomes a deuterium, grab another proton, becomes a helium-3, 2 helium-3s come together, make a helium-4 with 2 surplus protons. And so that's the process. Okay, it's using up hydrogen, 4 hydrogens, actually 6 hydrogens go in, and what comes out are 2 hydrogens and a helium. So ultimately, net result is 4 hydrogens have become a helium. So when the sun first formed, when it was a brand new star, by mass, about 75% of it was hydrogen. Well, now at the outer part of the star, it's still about 75% hydrogen, but in the core, near the middle of the sun here, where you've been doing all the fusing, you have less hydrogen. So it's really only about 30% or so hydrogen at the absolute center of the sun. Now, this is by weight. Remember, hydrogen weighs a lot more than does helium. So it's still just over 50% hydrogen by number of atoms. But this is still a major shift in the interior of the sun. And so this actually means something. The other thing that's happening here is that we've got at the very beginning, when the sun was about 20% hydrogen, it's now, by weight, like 60-something% hydrogen. Okay. And helium, rather. So it used to be about 25% helium to begin with, and now 60-something% helium at the center. Now, the outer part hadn't changed much. Okay. So the question is, what does all that hydrogen and helium do in the core of the sun, and how does that affect anything? So imagine deep inside the sun, you got the core, and you've got hydrogens in here. And remember, when the sun first started, then the hydrogens, for every like 9 hydrogen atoms, there was a helium atom. Okay, and so all these hydrogens in here, then a helium. Okay, and so what happens is you have all these hydrogens in here, and as they're doing their thing, then the heat and pressure is causing the hydrogens to fuse together, and they make a helium. Well, the result is that you end up with more and more heliums in here. Now, what effect does that have? Now remember, to do the proton-proton chain, the hydrogens have to be squeezed close together, and they have to be heated up so they run into each other. So when they run into each other, that gives you the fusion. And then you got to have another hydrogen fuse in order to make a helium-3. Now, here's the problem. All of these surplus heliums that are in there, all the surplus heliums are getting in the way. They're not part of the fusion process. They're just getting in the way. And that's keeping the hydrogens from bumping into each other and fuse. Now, we talked about how in the core of the sun, there's like a thermostat. The gravity is trying to squeeze the core smaller. But all the heat is trying to push outwards. Okay, so all the energy released by the nuclear fusion is pushing outwards. That's balancing gravity. Everything is stable, but if all those heliums are in there getting in the way, what that does is that causes the reaction rate to slow down. When it slows down, then what happens is that this outward pressure wins and squeezes the core just a tiny bit smaller. That heats it up, and it gets a little bit hotter. When it gets hotter, the fusion rate increases. Now, the fusion rate would have been just fine if we had the proper ratio of hydrogen-helium, but because all that helium was in the way, we weren't fusing fast enough. So we have to heat it up to speed up the fusion. If the core gets hotter, that means the mid layers of the sun are heating up, and they're going to expand. When they expand, they push on the outer part of the sun, and the outer part of the sun expands slightly. Okay, so we got a slight expansion. So the end result is that helium gets in the way, makes fusion run too slow. The built-in thermostat in the core makes the core squeeze a little bit smaller and hotter. That makes the fusion speed up to where it's supposed to be to hold up the sun against its own weight. The excess heat in that core is making the interior of the sun a little bit overheated, so it expands a little bit. That makes the sun get slightly bigger, but because we're speeding up the fusion process, it's slightly brighter. So the sun over time is actually getting bigger and brighter. It's probably close to about 40% brighter today than it was when it first formed. It's also about 5.5% hotter than when it first formed. So about 4.6 billion years ago, the sun was just a tiny bit smaller and was a tiny bit cooler. So this is the effect that's been happening here with the sun over the time that it's been there. Okay, and so that's just the natural effect that happens. In fact, we can sort of see this on the HR diagram that stars form near the zero age main sequence, but then over time they gradually drift, a little bit upwards. I guess the upwards, so a little bit hotter and brighter. So they drift a little bit off of that zero age main sequence. And so this would be an example of the Pleiades star cluster, where some of these stars, not all in a straight line, but some are a little clumped, and some have evolved just a tiny bit off of the main sequence. The sun's been doing that too, and will keep doing it. So the main sequence is not just a line that runs across the HR diagram, it's a band that runs across the HR diagram. Stars in the bottom of the band tend to be younger. Stars in the top of the band tends to be a little bit older.